Okay, so when we left off last time, I had asked you to answer these questions on your own independently. What is a covalent bond? Well, it's the sharing of electrons to fill the outer energy level. So we said with ionic bonding, electrons could be transferred. So metals lose electrons and the non-metals gain electrons, or they can share electrons. So either way, they end up filling up that outer energy level and having a full energy level of 8. Nonpolar molecules are exactly what their name says. They do not have poles. They do not have a positive or negative end. Covalent compounds are called molecules. Okay. What is a polar molecule? It has poles. That means it has a positive end and a negative end. What makes an atom polar? Well, it's electrons. So if the electrons are shared equally, then there's not going to be a positive end or a negative end. If one of them has the negatives more than the other, and that's where the negative end will be. So it's unequal sharing of electrons. Which type of molecules are always nonpolar? It's the ones where they're going to share equally. Where they always share equally is when they're exactly the same. They're like twins. So those would be those diatomic molecules that are always the same size. Now, I'm going to take a look at this chart that's in your notes. When the atoms bond, we said that they could share 1, 2, or 3 pairs of electrons. And it really depends on their oxidation number. So family 5 has an oxidation number of 3, and so it needs to share 3 electrons. Family 2 has an oxidation number of -2, so it needs to share 2 electrons. So 2 plus 6 is 8. And family 7 and hydrogen need to share 1 electron each. Family 7 has an oxidation number of 7, so it needs to share 1 electron to get to 8. And hydrogen over in family 1, if it shared 1 electron, it would have 2, which is that full first energy level. Now, each one of these little lines means that it's a bond. So the family 6 elements all need to make 2 bonds somehow. So they could make 2 single bonds. Okay, so they could bond singly with another atom. So that water has a single bond to a hydrogen and a single bond to another hydrogen. Or they can share 2 pairs together and have a double bond. Family 5 needs to share 3 pairs of electrons. So it could share, there's 3 different ways. It could share 1 pair individually 3 separate times. It could share 1 pair and then it could have a double bond, or it could share 3 pairs all together with 1 atom. And it could make a triple bond. And remember, we said atoms could make single bonds, which is this single line, double bond, which is represented by this double line, or a triple bond, which is represented by this triple line. Okay, and then each line represents a pair of electrons, one from one atom and one from another. When they're sharing, okay, each one puts in. So like that's what sharing is. So I share an electron with you and you share an electron with me. And family 4 can share 4 single bonds, 2 single bonds in a double, 1 single bond in a triple, or 2 double bonds. This is the only way the elements can really bond. Now, when they get put together, things have to match up, okay? They have to match up like pieces of toys. So, for example, chlorine is going to make a single bond, and that's all it can make is a single bond because it has 7 valence electrons. If it shares a pair, that would be 8. It can single bond to another chlorine. Okay, so this chlorine shares an electron with this one, and this one shares an electron with that one, and they both feel like they got 8 electrons. Okay, this does not work. Okay, chlorine can share a single bond, and the oxygen needs to share a double bond this way, so that the oxygen could not bond to the chlorine. Okay, the oxygen could share a single bond to the chlorine this way. Now, oxygen has 6 valence electrons. It's sharing 1 with the chlorine, so it takes care of the chlorine. chlorine has 7 plus the one it's sharing is 8. The oxygen has 6 plus the one that is sharing with this chlorine is 7, but it's still 1 electron short. So it needs to share with another chlorine. So these connections, the pieces need to all fit together when we make molecules. Okay. Oxygen can also form a double bond. It can double bond to another oxygen. So oxygen has its 6 valence electrons. It shares 2 with this one. So this one feels like it's got 6 plus 2 is 8. This one has 6, and this one is sharing 2 with it. So 6 plus 2 is 8. It cannot bond to a nitrogen. Nitrogen needs to share 3 electrons. It needs to make a triple bond. Oxygen can only share 2. It can only double bond. So this wouldn't work out, and you almost think of like pieces of toys that have to hook together. Okay. Now, oxygen can double bond to carbon. So carbon has 4 valence electrons. It's going to share 2 with the oxygen, so that's 6. But it still doesn't have that full outer energy level. It needs to share with another oxygen. So now the oxygen is sharing 2, it has 6 valence electrons. It's sharing 2 with the carbon. 6 plus 2 is 8. Carbon has 4 valence electrons. It's sharing 2 with this oxygen on the right. So 4 plus 2 is 6. And it has 2 that it's sharing with the other oxygen. So it has 6 with these 2, that's 8. And then the oxygen has 6 valence electrons, plus 2 is sharing with the carbon. Okay. We end up with CO2. Okay. Now, carbon can also single bond. Okay. The nitrogen can single bond this way, but it leaves it unbonded this way. So this wouldn't be a good matchup. There's nothing over here. Okay. Hydrogen over here, like chlorine, can single bond. So hydrogen has 1 valence electron. 2 is a full energy level. So this hydrogen is sharing 1 with the carbon, plus the 1 that it has, so that's 2. The carbon has 4 valence electrons, plus the 1 is sharing with the hydrogen is 5. So it needs to share with another hydrogen. And that would now be sharing 6. Now it would be sharing 7. And now it would be sharing 8. And you can see all the pieces hook up and nothing is left unhooked. So we want to keep that in mind as we move through these covalent compounds. So what is a covalent compound? They're formed when atoms share electrons that have a full outer energy level of 8 electrons. This is the same number as the oxidation number. The compound is called a molecule. In the last lesson, we talked about diatomic. Diatomic is 2. Di means 2, 2 atoms. So what is a 2-atom molecule? It's a covalently bonded compound with 2 of the same atoms. And the examples we said, O2, H2, and N2. Diatomic molecules are always nonpolar because the atoms are the same size, they are identical, and the electrons are shared equally. Remember we said sometimes the bigger atom picks on the little one and keeps the electron to itself most of the time. Covalent binary compounds or molecules. So how do we name them? Now remember, with the ionic compounds, we put the name of the first element and then the second one, and we put IDE on the end. Okay? This is pretty similar, except we use these Greek prefixes. Di, tri, tetra, pents, hexa. Or the second element, we add IDE. Okay? So di means 2, tri like a tricycle means 3, tetra means 4, pent like a pentagon is 5, hexa like a hexagon is 6. So here's an example. So we have carbon, and then there's 4 hydrogens. So we're going to say tetra, 4, and then hydride. We put IDE on the end of the second one, just like we did before. Here's another example. You have the name of the first element, which we never change. And then there's a 2. So there's the prefix comes before the element name. So we need to say 2 oxygens. So we say dioxide because we still put IDE on the end of the second element. Now you see that there's 2 phosphorus. So we need to say 2 phosphorus. So we say di. We never change the name of the first element. So we just say phosphorus. And then we see that there's a 4. So we need to say 4, which is tetra. For what? Oxide. This would be diphosphorus tetroxide. This one we see carbon. We see the 4. We're going to put the tetra. And then we put the name of the second element, which is fluorine, with the IDE on the end. So it would be carbon tetrafluoride. Okay. And then we're going to look at naming some elements and coming up with their structural diagrams. So if we bond a fluorine to a fluorine, we know that that is diatomic because it's going to be 2 fluorines bonded together. If it's diatomic, we know that it's going to be non-polar. Okay. If we look at the periodic table, we find that fluorine is in family 7. It needs to make 1 bond. It's the same as oxidation. Fluorine's in family 7. It means it has 7 dots in its dot diagram. It needs to make 1 bond. And the other fluorine is the same. Where it says number of atoms needed, you can, it's almost like crisscrossing the oxidation numbers. You can take this one and put it down here, and this one put it down here. What that's really asking is how many you need to put them together. You need 1 of each. You know, 1 left one and 1 right one. Okay. We said circle the smallest number of bonds because when we look at the chart, the 2 fluorines can only single bond to each other. So we got to make sure that the pieces match up. Okay. Look at his chart. Fluorine is in family 7, so it's going to single bond like this. So our fluorine is going to look like this. The other one's going to look like that. And now you can really see, like, yeah, we need 1 of these to hook to 1 of those. So we're going to take the one from the left, hook to the one to the right. When we look at this chart, single bond means 1 pair of electrons. 1 from the atom on the left, 1 from the atom on the right. Remember, they're sharing. So when we do the dot diagram, this single bond means a pair of shared electrons. So in order to make the dot diagram, we're going to take the 2 same element symbols. We're going to put in a pair of electrons. Now notice up on the dot diagrams, I had 1 fluorine was blue and the other one was black. Okay, and I really wanted to emphasize this. There's 1 blue electron from this fluorine that's being shared with 1 black electron from that fluorine. Okay, that's what we mean by a pair of electrons being shared. Okay, now the dot diagrams for fluorine are not complete. Fluorine needs to have 7 electrons in its dot diagram. This one has 1, and the blue one has 1. So we need to add in the rest of the dots to the dot diagram. 1, 2, 3, 4, 5, 6, 7. And that's all the 7 dots that we have up here. This one has 1, 2, 3, 4, 5, 6, 7. And now that's all the 7 dots that we have up here. Now you can see this is good because we have 8 balanced electrons around this fluorine. And we have 8 balanced electrons around this fluorine. And this is the pair that they're sharing. This is what's bonding them together. So in a structural diagram, it's represented by this single line. In the dot diagrams, it's represented this way. And what is our formula? Our formula is F2. There's two fluorines. So this is diatomic fluorine, like we said, and that's what its name is, difluoride, difluorine, because we never changed the name of the first element. Okay, now we bond an oxygen to an oxygen. We know that that's going to be diatomic. It's diatomic, it's going to be nonpolar. By the way, this is what we breathe. We're going to look at the periodic table. We find that oxygen is in family 6. So it has 6 valence electrons, and it needs to make 2 bonds or share 2 pairs of electrons to have 8. So it has family 6. It has 6 valence electrons. So it has 6 dots in this dot diagram. It needs to make 2 bonds in order to have 8 valence electrons. Okay, the other oxygen is the same. Now, since it's diatomic, okay, we're going to be using, in this case, it needs to form 2 bonds, right? We've got 6 valence electrons. It needs to share 2 pairs. So we're going to be double bonding these oxygens together. So let's take a look at this chart. Okay. Oxygen is in family 6, and it needs to make 2 bonds. Okay. We're looking at, these are our choices. And we said that it's going to double bond. So we're going to pick this kind of oxygen. So we need 1 on the left, is going to hook to 1 on the right, which makes sense because it's diatomic. So we're going to use a total of 2 oxygens. So we have O2, this is going to double bond this way. And O2, this is going to double bond the other one. And remember I said circle the smallest number of bonds. You can think about it, these are O2, so it doesn't matter. But that's what we're using in our diagram. We're using the one that matches here. This one doesn't match. Okay, this has single bonds. We said we needed double bonds. Okay, so now we hook them together. We take our oxygen from the left. We're going to look at the 1 oxygen on the right. Now we got to do the dot diagram. Okay, so we're going to take a look at this chart. The double bond means 2 pairs of electrons are being shared. 2 from one atom, 2 from the other atom. Okay, because they both need to get to 8. So this is represented by that. So what we want to do is we want to put down our element symbols. And we're going to put the bond in. There's the 2 electrons from the oxygen on the left, and the 2 electrons being shared from the oxygen on the right. Okay, now oxygen needs to have a total of 6 valence electrons. So we have 1, 2, 3, 4, 5, 6. And the other oxygen in its dot diagram up here is supposed to have 6 valence electrons. So we have 1, 2, 3, 4, 5, 6. Now, if we look, this oxygen has 1, 2, 3, 4, 5, 6, because they both count what they're sharing, 7, 8. This oxygen over here has 1, 2, 3, 4, 5, 6, 7, 8, because the electrons in the middle are being shared. So both of them think that they belong to each other. And the reason why I use the blue dots and the red dots is so that we can see that our dot diagrams are complete. Each one of them has the 6 dots that it's supposed to, and together they both feel like they got 8 valence electrons. And in the formula, well, we have 1, 2 O's, so the formula is O2, which makes sense because we said it was diatomic. Okay, there's oxygen bonded to an oxygen, and then the formula, the name of the compound, well, there's a 2, so that means it's a di. And if we don't change the name of the first element, then there's not a second one, so we're done. It's just dioxygen. Okay. We're going to take a look at one more, and then I'm going to let you practice No. In this case, we have an oxygen bonded to a hydrogen. And it's not diatomic because they're not the same. And we're going to decide that this must be polar. So we need to find oxygen and hydrogen on the periodic table. Here's oxygen in family 6, has 6 valence electrons. It needs to make 2 bonds. Okay. Hydrogen's over here in family 1. It has an oxidation number of 1 plus, and it needs to make 1 bond. Remember, the first energy level is filled when it has 2 electrons. So we have oxygen's in family 6, 6 valence electrons. 6 valence electrons means it has 6 dots in its dot diagram. Number of bonds is the same as the oxidation number, so it needs to make 2. Okay. The hydrogen is in family 1. It has 1 valence electron. It needs to make 1 bond. It's the same as the oxidation number. And it has 1 dot in its dot diagram. Now, the trick I said was circle the smallest number of bonds. Well, 1 is smaller than 2, so our diagram is going to use single bonds. That's because that's the only way hydrogen can bond is by sharing 1 valence electron. It can't share 2 because it didn't got 2. It can't share 3 because it hadn't got 3. It only has 1 valence electron that it can share. So the only way it can bond to the oxygen is with a single bond. Now the oxygen wants 2 bonds, so it's going to probably take 2 singles to satisfy the needs of the oxygen. Okay, so we're going to look at our chart, and we're going to look at the kinds of bonds the oxygen and the hydrogen are going to be using. Well, we have circled single bonds, so we're going to find oxygen is in family 6, and the only way family 6 can bond is it can make 2 single bonds, or it can make 1 double bond. Hydrogen is in like family 7 and hydrogen make 1 bond. Okay. Oxygen's over here. We're going to pick the single bonded oxygen because it matches this single bond here. Okay, this one doesn't match. This is a single, this is a double. Here we have 2 singles, so we got to match. Okay, for our hydrogen, it has to look like this. So now we got to think. And it's just like crisscrossing the oxidation numbers. We can take and put this 2 here, and we can take and put that 1 there. Okay. Our hydrogen looks like this, and our oxygen looks like that. Well, remember, we can't leave any pieces unhooked. So we're going to need a hydrogen to hook onto here. We're going to need another one to hook onto there. So we need 1 of these. We're going to need 2 of those. And again, remember, these are the oxidation numbers. You can take this 2 and move it down over here. You can take this 1 and move it down over there. So now, to do our line drawing, we have our oxygen. And we said we were going to need 2 hydrogens. We have 1 for here, and we have 1 for here. To our dot diagram, we remember that a single bond, okay, it represents a pair of electrons. So in order to make the dot diagram, we write down the same element symbols exactly the way we got them over here. And we remember that a single bond, this dash, is a pair of electrons. Okay? So it's 1 electron from the hydrogen and 1 electron from the oxygen, and they're sharing. So it goes in between it. So it's bonding them together as that sharing of electrons. So we're going to put in a pair of electrons for this bond and a pair of electrons for this bond. So we have a pair of electrons for that bond and a pair of electrons for the other bond. Okay? And that's what these single dashes mean. We need a pair of electrons. Now up here, each hydrogen is supposed to have 1 valence electron. And I put them in colors so we can see. Hydrogen has all the valence electrons it's supposed to. And the other hydrogen has all the electrons it's supposed to. But each oxygen is supposed to have 8 dots. And each of our oxygen only has 2. So we need 3, 4, 5, 6. Now it has, this one has 6 dots, and this has its 6 black dots. And look what happened. Around the oxygen, we have a full energy level of 8. And then for each hydrogen, we have a full energy level of 2, which is that one full first energy level. Now, the formula for this is 2 H's and 1 O. So look at what we've named water. Okay. Now, if we want to name the compound, the name of this compound is there's a 2, so the prefix is di. We do not change the name of the first element, so it's hydrogen. And then we put ITE on the end of the second one. So it's dihydrogen oxide. And we're going to pick up here next time. But right now, we're going to stop and I'm going to let you do some of these on your own.